Welcome back. Today we are going to start equivalent self-inductance of a group of coils. First of all, when coils are connected in series. So here are two coils. We have here the two inductors. Its self-inductance is L1 and its self-inductance is L2. N's are denoted here A, B and C. C is the joint of L1 and L2. So potential difference across A and B is epsilon. Potential difference between this is epsilon 1. Potential difference between these two is epsilon 2. So potential difference across A and B is epsilon. Epsilon is the potential difference between A and C, means across the inductor which has its self-inductance L1, and epsilon 2 is the potential difference across L2. So we know here that epsilon is equals to minus L di by dt. Minus L di by dt. This will be equals to I is the current flowing through all this combination. So this is E1, that will be equals to minus L1 di by dt, and E2 equals to as the same minus L2 di by dt. Now solving this, we will find L equals to L1 plus L2. So here we will find L is the equivalent self-inductance of these two coils when they are connected in series. So this will be equals to the sum of the inductance of this and this. So equivalent inductance will be equals to L equals to L1 plus L2. L1 for this, L2 for this. Now we are going to see the coil connected in parallel. Here is one inductor, this is the another inductor. They are connected in parallel. Its self-inductance is L1 and its self-inductance is L2. Now supply a current I. Now at this point it is distributed in L1 and in L2, and current flowing through this and through this. That will be different. From here it is suppose I1, and through this current I2 flows. So here we will find that I equals to I1 plus I2. This is. Now we will differentiate this with respect to t, time. So this side di by dt, this equals to di1 by dt and plus di2 by dt. So we will get this. But we know here the EMF between this and this. So EMF across this, that will be equals to minus L di by dt. This is for the whole combination. So we will see that epsilon naught is the potential difference across this and this, and L is the equivalent inductance of both these two coils. So from this equation we can write di by dt is equals to minus epsilon by L. So we can write, similarly we can write this di1 by dt, this equals to minus epsilon by L. Remember here that epsilon is the potential difference across these two also. So, and this is di2 by dt, this equals to minus epsilon by L. Here now, this is for L1, this is for L2. So we can put the values here. This is di, this is this. Then we can write here now for this one di by dt here in this equation. This is from 1 minus this by L for this one here equals to minus epsilon by this for this one from here minus this by L1. So we can write 1 by L equals to 1 by L1 plus 1 by L2. Now this is here L1 L2, then L1 plus L2. So L equals to, this is L1 L2 by L1 plus L2. This is the equivalent inductance, self-inductance of these two coils when they are in parallel. So now we are going to discuss here the new portion, new topic here, that energy is stored in an inductor. Definitely energy is stored when a current flows through a conductor. We will see then a magnetic field is induced around this. So we will see that magnetic energy here. So energy is stored in an inductor. First of all, we will take an inductor. This is here one inductor which in the self-inductance is L, and we will connect it through a power source, a battery, a key. This is the battery, this is the key, and this is the inductor L. Suppose I current flows through this and potential difference across this is equals to, suppose, VL. Then what will happen? If I current flows through that inductor. So an EMF epsilon naught is induced in this inductor in opposite direction. So this equals to minus L di by dt. So EMF induced, this is equals to minus L di by dt. This is. Here we will see the negative sign. Negative sign shows that epsilon EMF induced opposes EMF induced in this inductor opposes the current I in this inductor. So now to derive the current through this inductor, we have to apply an external voltage. So here external voltage must be equals to this. This is the external voltage. So this voltage we have to apply by this battery to drive the current through this inductor. Now suppose when current flows, then a very small charge dq passes through this inductor due to this. So now this time work done by the external supply by this battery is suppose dW, and we know very well dW equals to VQ. So here applied voltage is this into dQ. Now we will put the value of epsilon from here. This will be equals to L di by dt dq. Now we can take out from here L di now dq by dt, and we know very well dq by dt I equals to dq by dt. So this may be written as L di I. So this equals to L I di. This is the work done by this applied EMF in passing dq current, a dq charge through this inductor. Now we know very well dW equals to this work done. Now we are going to find out the total work done when it maintain maximum value of current. So we have to integrate this. Then integration of dW is equals to integration of L I di. So here 0 is the minimum current and suppose I naught is the maximum current. Here we will take out the constant L which will be not change, then L integration of I di, and this will be integration of this, that will be here L I here square by 2 and taking the limit this will be equals to L, this is I naught square by 2 minus 0 square by 2. So work done W, that will be equals to L I naught square by 2. This is here the work done. This may be written as 1 by 2 L I naught square. So this is the work done. So work done is, or we can say that work done in increasing the current flowing through this inductor is magnetic potential, that will be denoted by U here like that. So that will be equals to half L I naught square. This is here the magnetic energy stored in the inductor. Now we will see some more expression for this magnetic energy. We know here B equals to magnetic field. This equals to mu naught N. N is the number of turns into the current flowing through this. So I naught is equals to, from this equation, B by mu naught N. We know also that inductance, self-inductance, this equals to mu naught N square AL. Where this L is the length of the solenoid, length of the inductor, and A is the area of the solenoid or the inductor. Putting this all in this one, this equals to 1 by 2, putting the value of L, mu naught N square AL into value of this from here. This is B square by mu naught square N square. Here we will see these two N square will be cancelled, and 1 mu naught here from here, that will be cancelled. Here we will find 1 by 2, this is cancelled. Here B square, this AL by mu naught. This is here the another expression for the magnetic energy stored in the solenoid. Thank you.